go at, because we had somewhat similar objectives, but didn't quite get as far. But I'll have, so our goal was to look at the June ice field, and the approach that we took is to take the things we learned, like how to get data and do some of the analysis that Dave Sheen showed us, and just apply that to one particular area. And also with simplification in mind, so that in particularly Seth, who's heavily involved in the June ice field program, wants to use this with undergraduate students, maybe the kind of students who think that posting something on Instagram is programming. So we try to keep this as simple as possible. So that's what we had in mind here. Before I start, I just want to share something. This morning when Anthony got his birthday cake, reminded me of an episode years ago when he was a grad student and his advisor Keith Heckelmeyer showed up with a birthday cake and made us all sing happy birthday, and was extremely disappointed when he found out that it was nowhere near Anthony's birthday that day. Okay, anyway, with that, I'll pass on. So one thing we do have is probably the prettiest picture of all the presentations, so there's something here. And we'll just kind of go through various things we did this week, and I'll start with Seth.
Yeah, so I'll start. One of the nice things about the June ice field is it has a really long record retreat. This is a more recent paper that came out just kind of showing retreat. And one of the interesting things about the June ice field is you have the Taku Glacier, which has been actually gaining mass for a number of years, but we recently have recognized it is, in fact, now retreating. This is a record that Chris McNeil and Chad O'Neill have finished up just recently, and they're about to submit it for publication. But it basically shows a long-term reanalysis of mass balance data from the 1940s until now. You can see the Taku Glacier had been advancing and now is in retreat, and the Lemon Creek Glacier has lost about 40 meters of elevation over that time period. And some obvious features that you see. This is a classic Gilkey Trench on the ice field, and between 2001 and 2017, again, lost about 40 meters of elevation, also losing amplitudes of the beautiful ogives that you see. So we have a lot of information like that on the ice field. And we also have the benefit of having a 2-month program every summer. This year, we have about 84 people coming to the ice, 32 undergrad students. We have 8 graduate students and postdocs doing research on the ice field as part of their research, teaching research faculty coming from 20 institutions, and 8 funded projects doing work on the ice field. So a pretty collaborative effort. And so I kind of compared it to, like, imagine all of us being in the field together for two months doing this, but in the field setting is basically how JERP runs now. So the idea behind this, I've been bugging Martin for probably a couple years now. He might get guessing me, maybe that's why he agreed to do this, is to focus on the Juneau ice field as kind of a test case for smaller mountain glacier systems, ice caps, ice fields, as opposed to Greenland and Antarctica, because we have this great infrastructure and this long history and the ability to kind of spend a lot of time up there in the ice field to do more sophisticated studies. These are a few slides of just a few of the field camps that we have across the ice field. And so this is a group of some of the scientists coming up to the ice this year to do a number of field tests. Kristen Pointer's here, she's doing some work up there. Daniel Shapiro, who just left, is bringing numerical modeling to the ice. And we've divided kind of teams into different locations, collaboratively working with each other. And this is an example of some radar work where we found a nice aquifer. And we know it's an aquifer. Oh, I don't know what the request means, but try that. Okay, well, it's not going to show, but that's a core dripping wet, so similar to the Greenland aquifers that we see. And one of the main points we're trying to do is kind of tease out the mass balance structure and the glacier hydrology components across the ice field. So with that, glaciersat2 is a valuable information that we plan to use. So we try to design some very simple tools that students can use, just working with the Earth data portal, and also working with the open altimetry to learn how to access the data. And again, our students range from really heavy STEM science background to almost none at all. So we wanted to start really simple with having students kind of using these access options to access the data and compare it to the existing data sets we have on the ice field. And then from there, we jump into the more complex stuff that we've been doing.
Actually, you were going to go next.
So I don't know about more complex, but so I mostly worked on adapting the nice tutorials that Amy put together for accessing the ISAT2 data, and then that Fernando put together to downsize that ISAT2 data to the variables of interest. And then I was really focused on converting the .h5 file that came out of Fernando's tutorial to a .csv that the students at JERP this summer could play with and analyze. And so I thought it would be useful for the room to just show a couple snippets of code that managed to accomplish that. And then I also made an effort to provide some information in the Jupyter notebook about the origin of the tutorial. So I just included that the original tutorial was developed by the original author and that it had been adapted by myself. But to speak to the point made earlier, having something to actually cite, I think would be really cool and interesting for whatever comes off of the ice field. Thank you.
You're not going to go through them. Okay. So the part 3 we have here is something that I called Sheen to Chirp. So I tried to adopt a lot of, how do you increase the font here? Okay. So the idea here was to go through and do some of the things we learned in the part that Dave showed. So download an Arctic DM tile, download ISAT tracks, overlay them, which involves some reprojection because one of them, luckily they're both in the same vertical datum. They both use WGS84, but the Arctic DM is in polar stereographic. ISAT tracks aren't that long, and then calculate elevation changes. So that was the basic idea here. So we adapted those notebooks. We downloaded the Arctic DM just in here, and just to see that it's actually there. That's how that particular tile looks like. It's not very informative because I think the should actually be stretched. It's only 5 kilometers wide, but 40 kilometers long. So the axis here are pixels. But then we took the ISAT tracks, calculated, interpolated to basically just what Dave was showing us, interpolated the DM to the ice track positions. So these are a set of we looked at all the beams, and these are in color here, the DH to the Arctic DM. So blue is where the ISAT track is higher. And this is I already cut the range to plus minus 10 meters. Because there's all sorts of clouds and things in there. There are big mountains that apparently grew. And this figure shows all of those data points. So it shows that definitely there's a lot of, I know what do you call that, Dave? The remote sensing reality check has not happened here. Maybe an indication that there's a spatial bias here. There seems to be more blue here and more red here. So there's definitely some artifacts in the data that we haven't had time to look into. But maybe the most interesting thing we managed to do is to produce this histogram, which is an histogram of, on the x-axis showing elevation change, and it's just been the elevation change. David showed that same thing. But when we looked at the ISAT tracks, we saw that there were 4 different times when ISAT grazed over that particular tile. And so if you just spin by time, you see that at least the mean here shifts over time. So the earliest one is this one here. It's unfortunately, I have them in reverse order. This is days since January 2018. Is that right? Is that how ISAT time is? second since, yeah, okay. So this would be kind of in October. You see that at that time you center pretty well. I don't actually know what the date for the Arctic DEM is because these mosaics, it's a little bit tough to find out, and I haven't quite gotten there. But then you see a shift towards the negative, and then a large shift. So the second to last overflight is in orange, and then the last one is in blue. So that shifts back to positive, which probably just indicates snowfall, I would assume. But that's about as far as we've gotten with the analysis. And I just want to acknowledge here, so this is the last thing I have to show. I want to acknowledge all the help we got from Rob and Tyler and Dave and Ben as well. So we've had some pretty heavy data scientist involvement, which was much appreciated.
So I just wanted to add two things. First of all, it's really great to see this Hack Week in comparison to some others, because with this focus in this community, I've seen you make a lot of progress relative to other Hack Weeks, which can be more spread out. And as the tech that underpinned this thing was kind of supported by Pangeo, it's also going to be to Pangeo's advantage to be able to bring together the tools that you developed and present that as part of the NASA payoff, kind of the ability to increase access to NASA data sets. This is all really great virtuous cycle. And in case it doesn't come up, if you were eating lunch tomorrow and think, oh, dang, I could have been planning proposals, with the amount of time we have left, it might be valuable to get together with like-minded people and think about proposals that can write if this machine keeps working this well.